Bismillahirrahmanirrahim. Assalamualaikum warahmatullahi wabarakatuh. Hi class, welcome back to SIC2006. Today we're going to proceed with lecture 5. But before that, let's recap what we have covered last week in lecture 4. We talked on what happened when the nucleus beams actually felt the applied magnetic field, and so it goes through this spin precession, and which led to two kinds of relaxations, which is the longitudinal and transverse relaxation. Okay, and so I also shared with you how do you actually define the line width of a spectrum. So you just take the line width at half the height of the peak, and so that's defined as a line width of a spectrum. And with the line width of a spectrum and various spectra as well, you can do various analysis to understand the materials that you're studying. Okay, so if this doesn't ring a bell, so I hope that you look back at the notes. Okay, so really today what I'm going to share with you is on chemical shift. But of course, there are extra just for extra knowledge for you. Now, so if, this is just hypothetical. If a molecule just contains one hydrogen atom, so you can expect that you will only see one absorption line. But of course, molecules do not have just a single atom, For example, proton, it has other nuclei as well. And so it's really, in terms of the NMR spectrum, you can expect that, it's much more complex than seeing just one single absorption line. So as you can see here, these are examples. This is an example of the kind of NMR spectrum that you will see. And so, it doesn't really involve that. There's a lot more in the process. So so it's important to know on chemical shifts, spin-spin coupling, and exchange process, because that actually sort of like give a way for you to understand the molecular structure of a compound. So we talk about the applied magnetic field, but the field experienced by a nucleus, which usually is called a local field, is not the same as the applied field because of the electrons surrounding the nucleus. Now that's why NMR is such a powerful tool, because if a molecule, you have a molecular structure, and all the atoms actually experience the same applied magnetic field, the same field, okay, you disregard their electronic structure, the electronic surroundings. So for every molecule that you actually put inside the NMR spectrum, the NMR spectrometer, you will just see a single line, because if there is no no difference, if they feel all the atoms in a molecule feel the same magnetic field, so it's just going to give a single line, and the same is true if you put any molecule, any compound in the spectrometer, it's just going to see a single line. So then that makes NMR spectrometer really useless, and not as claimed as it's being powerful. So surely it's more than that. And so that's why the magnetic field experienced by the nucleus, the local field, is not the same as the applied field because of the electrons, the surroundings, because each atom will actually have different neighbors, and so they have different interactions and so on. And so this local field is actually related to what we call this shielding constant. and that will actually, whether it's being shielded or deshielded by it's being shielded or deshielded, that will actually govern the the chemical shift that you're going to see. Okay, so really, so you may have this the field from the magnet, and then you have this shielding from the electrons. Okay, and so the effective field that's actually experienced by protons. So this is just a cartoon diagram to show that because of the electronic neighboring, so the atoms will actually feel, different atoms will actually experience different field, effective field. Although, at large, you have this, applied magnetic field from the magnet. Okay, and that's why it is a powerful tool, because if different atoms start experiencing different effective field, then you get these different absorption lines at different chemical shift, and from there you can actually elucidate the molecular structure. If you don't have this, then if every atom actually experiences the same effective field, then it doesn't make sense. So this is this is really a useless tool. But fortunately that's not the case. So that's why this is really, really a powerful tool to elucidate your molecular structure. So, all right, so that's that. So this is again extra. So it depends on this the values of this shielding factor, and so because of that, the resonance frequency is also going to be affected by this shielding factor. Okay, so this is the gist of today's lecture, really, and I want you, the main equation that I want you to focus on is this, and please remember this equation. Okay, so the resonant frequencies can be expressed in terms of a quantity called the chemical shift, which is related to the difference between the resonance frequency of the nucleus interest and the resonance frequency of a nucleus in a reference substance. Okay, so and the reference is usually this tetramethylsilane. I will talk about that in a little bit. So this is the chemical shift, and it's usually in ppm for this proton NMR and carbon-13 as well. So this is actually the frequency of your nucleus, and this is the frequency of the TMS, which is, of course, this is going to be 0, and then this is the frequency of the spectrometer. Okay, and the unit for the chemical shift is in ppm. So this is in hertz, and this is megahertz, and make sure that you actually convert that when you want to do this calculation. So this is the equation to remember. So really the gist of today's lecture is just on this. Okay, so why is tetramethylsilane used as the reference? Okay, so it's because when you actually put that along with your sample, you want to make sure that it doesn't disturb the signal of your sample. So this TMS actually is soluble in most organic solvent. It's inert, and that's important so that it doesn't disturb the signal of your sample. Highly volatile, and so it evaporates easily. So if, for example, the synthesis of your sample of your compound is really, really very complicated, and the amount that you get, amount of yield that you produce is very small, so no problem. You can actually recover it and use the same sample to run to test on other techniques. Okay, and there are 12 hydrogen atoms, as you can see here, and they are all in the same environment. So because they are in the same environment, so you only see a single strong peak in NMR at 0 ppm. Okay, and the electrons in the CH bonds are closer to hydrogens than in almost any other. That means that these hydrogen nuclei are the most shielded from external field. So really, this is the reason why TMS is used as the reference. Now, the advantage of why we use, for example, in evaluating the chemical shift, why you use the ppm scale is that it is actually independent of the strength of the applied field. Okay, and because of the nature of the numerator denominator is proportional to applied field. Okay, but if it's reported in hertz, okay, that's dependent on the applied field. Now this is important, especially if you have collaborators, and if you have a collaborator in Japan who has a who has an NMR spectrometer at 600 megahertz, and if you only have a spectrometer of a 400 megahertz, so if you run, for example, sample A, and you get one of the, if the chemical shift, for example, of one of the peaks is at 4 ppm. So if you run it, your collaborators run the same sample, so the shift will, despite using a higher spectrometer, okay, it's still going to read 4 ppm for that particular peak. So in terms of, this makes it very easy in terms of discussion, in terms of comparison, and so that's why ppm is chosen. Okay, and so here's an example. If a nucleus with a chemical shift of 1 ppm in a spectrometer, you're operating at this 500 megahertz, or the magnetic field is equivalent to 11.75. So according to this equation, so this will have a shift relative to the reference at 500 hertz. Okay, the same nucleus in a spectrometer in 100 megahertz, the shift relative to the reference will be 100 hertz. So, so you see here, if it's in hertz, it's going to be different. But as you can see here, when you actually use the chemical shift in ppm, it retains the value. So remember, the whatever spectrometer that you use, whatever strength that you use, 400 or 600 megahertz or 300 megahertz, the ppm, the value of the chemical shift in ppm doesn't change. Okay, so usually I ask you questions at the end of the slides, but this time I'll give you in the middle. Okay, so given that the the frequency of the nucleus of the proton is 180 hertz, and the spectrometer's frequency is 60 megahertz. So calculate the value of the chemical shift. Okay, and if the spectrometer used is changed to 100 megahertz, what will be the value of this frequency of this proton? So do that as an exercise to show that you understand. Okay, so then this is the equation. This is the only equation that you have to play around with. Okay, so I can actually end the lecture here, but I just want to share with you some knowledge so that you get a better understanding of this. Okay, so For chemical shift larger than 0, that means larger than that of the TMS. If the electron density around a nucleus decreases, so the opposing magnetic field becomes small, okay? And so you will actually feel more of the external field. And so you have this deshielded. And when it's deshielded, you will have a higher chemical shift, higher ppm. It's moving this way. The TMS is at 0 here. And so this is where you have your nucleus or nuclei being deshielded. Okay, so because the electron density decreases. Okay, so I like this because this is really an overview. You've seen this equation before, and of course this tells doesn't show that this is the Zeeman splitting. Okay, and you know that because the Zeeman splitting is what you call proportional to the magnetic field that you apply. So the larger local field means you have larger Zeeman splitting. Okay, that means you have larger energy there. So the electron shields the nucleus from the external field. So you decrease the local field. So when you have that more electrons, that's going to shield it, and when that shield it, you decrease the local field, and when that reduces, the energy also reduces, and you have smaller Zeeman splitting. So this is the case when you have it shielded, and this is the case when you have it deshielded. So this is the shielding. You have larger chemical shift, increasing chemical shift, and this is moving towards shielding. Okay, so of course in various textbooks you have in terms of the overview, there are different overview. You have a choice to choose which one that suits you, that makes it easier. So I'm just sharing you this one example. And for any textbook, particularly organic chemistry textbook, this is something that you will see usually as one of the appendices at the back, or it may also be part, but usually it's the appendix. Okay, so you will see a guide to these are different, a guide to this proton NMR, the chemical shift values, which depends on this. You have different structure here. You have different functional groups. So different functional groups will actually give you a different chemical shift. And so this is the reason NMR is a powerful tool, because if all these functional groups feel or experience the same magnetic field throughout, so there will not be this guideline. You will only see a single peak, but because they experience different magnetic field, different field, different effective field, so you see them at various different locations of the chemical shift. Okay, and you also have for the carbon-13 guide for the chemical shift values, because usually the carbon-13 is complementary to that of the proton NMR, and we're going to talk that when we touch a little bit on carbon-13 in the coming lecture. What can we actually deduce from this? Okay, the easiest example for compound, the classic example is the ethanol, which has three different kinds of environment here. You have here the CH3 protons, you have the CH2 protons, and you have the OH proton. And on top of that, you have 3 protons here, 2 protons here, and 1 proton here. Okay, and so the relative intensities of the signal can be determined by the integration of the signal. So when you do the proton NMR, when you do the integration will actually tell the values, the number of protons you have in a particular group. So as you can see here. Right, so what can we deduce from this proton NMR? So there are four important information that you can deduce from proton NMR. The number of signals tells you how many different types of hydrogens there are in a molecule. And the position of the signals will tell you what types of hydrogens there are in your molecule. And the integration, as we've seen just now, will tell you how many hydrogens of each type of protons that you have. And what we're going to cover in the coming lecture is on the splitting pattern, okay, the coupling pattern, okay, how many neighboring hydrogens there are. So, you know, these are really what you call this is a very comprehensive information that you can actually get from this proton NMR. Makes it such a useful tool to actually finally resolve or find out or deduce or elucidate what's the molecular structure, especially if you synthesize something and you're not sure what's the molecular structure and you have an unknown. So the NMR will actually help that. Okay, so these are just extra. So shielding constant, the source of it can come from the contribution from the electrons. It can come from the rest of the atoms, the groups of atoms in the molecule, and it can also come from the solvent. And on top of that, there's also the diamagnetic contribution, which opposes the magnetic field and hence shield the nucleus, and you also have the paramagnetic field. So I'm not going to talk this in detail, but I just want to share with you this information that so that you know that if you want to know in depth of the NMR and so on, especially if you're doing really thorough work on NMR, this may be useful. And so I'm just sharing with you this information so that if you see this, you know, that will not be the first time that you see this, that you know that contributions of the shielding constant, you know, comes from various parts. Okay, and so one of the things, so I'm going to skip this. So the other thing that it's also important in this part is since we talk about this chemical shift and what actually shields it or deshield it. So one of the factor that will actually deshield it is the electronegativity. And so if you have a trend, for example, as you can see here, you see that the electron density on the proton decreases downwards because you see that you have, for example, chloroform with 3 electronegative chlorine here. It actually reduces the electron density, and so that will actually deshield. And it will resonate at high chemical shift. So if anything, you know, that I will concentrate on is on this electron withdrawing group. Okay, so to summarize that, electron releasing group or atom shields the nucleus. So you have releasing electron density to the neighboring atoms. Okay, an electron withdrawing group deshields the nucleus. Sorry, that's the wrong spelling here. And we will draw the electron density. And so you have high chemical shift. Yeah, this is also something that you may have seen in your organic chemistry textbook, because organic chemistry also talks about NMR, but in different aspects, slightly different from what we cover. Okay, you have this also contribution arises from the current induced in nearby groups, and this is known as the anisotropic magnetic susceptibility effect. So the induced current will generate a magnetic field that shield or deshield the nucleus of interest depending on the position of the nucleus relative to its neighbor. So it depends on the kind of bonds that you have. So you have here so depending on whether you have a triple bond or pi bond, you will actually indicate whether it's a shielding or deshielding region. And you have, for example, the famous one will be the benzene ring. So you have the anisotropic field. So you have here the pi bonds. You have here the area where you have it shielding. You have the area where it's deshielding. So you have here the ring current. You have the circulation of electrons around the field. So protons attached to the benzene ring are deshielded, whereas that lie below and above the ring are shielded. So this is something that I'm just sharing again, so that you know that the sources of having it shielded or deshielded, there are various sources, okay, not unique to electron withdrawing group and so on. And there's actually more to this, of course, but my focus will be on the electron withdrawing group, so do look at that, okay. So in other words, it's actually good to read your organic chemistry textbook when it actually touches on NMR, especially on these ring currents and so on the pi bonds and the pi system, and so you get a better feel of this, okay. Now, solvent can actually also influence the local magnetic field, so that's why it's important to actually choose inert solvents so that it doesn't disturb the signal of your molecule of interest, okay. This is again extra, and this is particularly for the solid state NMR. Now remember, I told you earlier in the early lectures, when our focus is on liquid state NMR, but there's also solid state NMR. So when you talk about solid state NMR, there's this thing called the chemical shift anisotropy. So the orientation of the nucleus with respect to the external field actually makes a difference. So if you have this orientation versus this orientation, it will actually give a different shift. But in liquid state NMR, we have this, tumbling of the liquid, so it's isotropic. So all the physical entities actually averages out, so you don't have this effect. Okay, so pretty much that's what I want to cover today in the lecture 5. So focus on the equation of the chemical shift, and remember that despite using different magnetic field, the applied magnetic field for different spectrometer, for example, as I said, 500, 400, 600, the chemical shift in ppm will always be the same, but if it's in hertz, it will be different. And then study on the effect of the electron withdrawing group, with respect to the chemical shift. Okay, and the rest of the information are extra information so that you have, a better understanding on this chemical shift and what actually governs it. All right, so that's all. Stay safe wherever you are, and for those who are actually not getting the gist of what we have covered before this, please look back at all this, the lecture notes, and go through all, and do the questions, because the questions that I ask in every lecture actually help you to better understand. If you can't answer the question, that means you have to reread to understand. Okay, so take care and bye for now. Assalamualaikum warahmatullahi wabarakatuh.